Hi everyone, this is the introduction to chapter 8.7, the Doppler effect of light. We've seen in chapter 3, sound wave, that if we have a source emitting a sound and an observer receiving that sound or measuring that sound, and there's a velocity relative to each other, that the frequency or wavelength measured by the observer will change. Well, we can see the same effect with light. If, for instance, we are on Earth observing a star with a telescope, and that star is moving away from us, well, the wavelength observed will be longer. We call this a red shift because red light is longer than blue light. The inverse, if we have the star coming closer to Earth, moving toward Earth, the wavelength will be shorter. We call this a blue shift, again, because the blue light is shorter than the red light. All right, so mathematically, it can be expressed using that formula for the wavelength. So the wavelength observed is equal to the source, the wavelength at the source, multiplied by the square root of 1 plus velocity divided by speed of light, divided by 1 minus the velocity divided by the speed of light. So fairly simple. It's really similar to the Doppler formula in the sound wave section. Now, one catch that is not obvious at first is how do we determine the sign of the velocity? And by we use the velocity is considered to be positive if the distance between the source and where the light is observed is increasing. So if the distance is increasing, we consider the velocity to be positive. The inverse, if the distance between, let's say, a star and a telescope on planet Earth, the distance is decreasing, we consider the velocity to be negative in this case. And keep in mind that we need to take into account the plus or minus here when we deal with the sign here. We will see many examples of these in the example after this video. Lastly, remember we've seen in traveling wave that the velocity of a wave is equal to the wavelength multiplied by the frequency. Here we are talking about a light wave. We know by now that light travels at the speed of light, c. So the speed of light has to equal the wavelength observed multiplied by the frequency observed, and is also equal to the wavelength of the source multiplied by the frequency of the source. If you were to combine the formula over here with this one, we could get an expression for the frequency observed with respect to the frequency at the source. Basically, it's nearly the same formula. They use the same convention for the velocity. The only difference is the plus or minus are inverted. That's it. All right, so in the next video, we are going to be solving some problem using this formula, and we're going to discover how some astronomers are using this technique in order to discover other planets around other stars. All right, so see you in the next video.